Hi everyone, this is Prof. K speaking, and today we're going to talk about reaction mechanisms. The learning objectives for today are to be able to distinguish net reactions from elementary reactions, which I'll define. We also want to be able to identify the molecularity of elementary reactions, and using these, write balanced chemical equations for a process given reaction mechanisms, and derive rate laws consistent with given reaction mechanisms. So before we start to use this language in the context of reactions, I just want to tell you what we mean when we say net reaction, reaction mechanism, and elementary reaction. So a net reaction is a balanced reaction or equation that indicates the reactants and products, but does not reveal how the reaction happens. And so most of the reactions that we've handled so far in this general chemistry course have been reactions that are best described as net reactions. They describe the reactants that go into a system and the products that come out of that system. The reaction mechanism, on the other hand, tells you a precise step-by-step process by which a reaction occurs. So this is more detailed than a net reaction and often looks different than a net reaction because it's telling you what's actually happening at the chemical level and what's actually interacting to generate the products. Elementary reactions are the individual steps that make up the reaction mechanism. And these elementary reactions individually represent something that's actually chemically happening. So far in this course, we've talked a lot about net reactions. And so if you put two ozones into some space, they can decompose and form three O2s. And if we were to take this net reaction as a mechanism instead of just the net reaction, and this net reactions aren't mechanisms, I'm just going to show you what we would predict would happen based on this expression. So you have two O3s over here hanging out. They come closer together, they interact potentially, and out pop three O2s. And so if we thought that that's what happens, then we could say maybe that is our mechanism. However, if we propose an actual reaction mechanism, it might be that you do still have the same two original ozones that you started with in your net reaction, but maybe one of them falls apart to form O2 and an oxygen atom. And then that oxygen atom goes on to interact with O3 and form another O2. So the net reaction for this particular mechanism would be the same. You still start with two O3s and you end with three O2s. But the actual chemical steps that are happening in your beaker are different. And so we have to be careful when we're talking about something as just the net reaction, or we put something in, we get something out, and what is actually happening from a mechanistic perspective. And occasionally it might be the case that the net reaction matches the reaction mechanism. But we don't know that before we look at experimental data, before we try to figure out what possible reaction mechanisms are, maybe before we look at possible transition states in this system. And so just be careful that when you look at a net reaction, you don't know what's happening in that system yet. And so this is the difference between a net reaction and a reaction mechanism. And then I wanted to remind you of the other piece of vocab I used before, which is that the elementary reactions are these two steps that make up our reaction mechanism that actually describe chemical reactions that are happening in our system. They help us figure out what a transition state might look like. So for the first elementary step in this reaction mechanism, one ozone molecule, O3, is hanging out by itself and it falls apart. So its transition state will have one ozone molecule potentially starting to fall apart. In the second line, an oxygen that was produced by the first step will encounter the other ozone molecule, and together they'll fall apart into two O2s. So the transition state of this second elementary reaction is going to involve an oxygen and an ozone molecule interacting. So these elementary reactions help us better understand what's actually happening in a beaker, in a system, whatever you're looking at, and describe what's going on step by step. And something that you'll notice is that the production of this oxygen atom isn't something you see in the net reaction. And that's because even though it's produced by this first step, it's immediately consumed by the second step or consumed at some point later in time by the second step. So the net reaction doesn't notice potentially that you produce this oxygen. And we have a specific name for this oxygen, which is an intermediate. And so in this expression, oxygen by itself is an intermediate, or a species that is produced in one step of a reaction and then consumed in a subsequent step in some particular mechanism. And so in the experimental sort of context of this problem, if while we're watching this reaction happen, we notice some new molecule like oxygen appearing, then that might suggest to us what sort of mechanism is happening or what sort of substeps are making up this net reaction. And so intermediates are different than transition states and are often something we can notice if they don't disappear too quickly. And so whether they disappear too quickly depends on how fast maybe the second step is. But an intermediate is like a reactant or a product, and it has some stability, but it's being produced somewhere and then being consumed elsewhere. So it doesn't show up in the net reaction. And so the reason that it's useful to sort of be able to navigate these expressions and use this language is because we can then start to talk about how our goal of trying to define rates of reactions can be helped by looking at individual elementary steps and their rates. And so if you wanted to determine the rate of some net reaction, you can't write it down based on this expression. You can't use the stoichiometric coefficients, and you can't write it down immediately. Instead, we do some rate experiments. So maybe we change how much ozone we have in our system, and we see how our rate varies with respect to ozone. And so that is the best tool we have for trying to describe what a rate looks like for a net reaction. Once we start writing these elementary reactions or elementary steps, we do know what's happening chemically and what's actually occurring in the beaker. So we can write down what the rate is with respect to the reaction. And so the rate of this first expression, this first reaction, is going to be the rate constant of that reaction multiplied by the concentration of O3, because that is the only species participating in the reaction. The rate of the second expression is going to be K2, its rate constant, multiplied by the concentration of this intermediate and O3. And so this doesn't immediately tell us what the total rate is, but it can maybe help us better understand what's happening. And we can use this to then try to predict what the rates look like, even if we can't be certain that they're true. And I'll talk about that more in just a second. But before we get too much into predicting rates from these mechanisms, I want to introduce some official language that I've sort of been describing but haven't officially named yet. And so in these reactions, we can talk about molecularity, which is the number of reactant entities. So if we have an elementary step that looks like A goes to B plus C, then it's unimolecular because it only has a single reactant and thus has a rate that's just based on its rate constant and the concentration of A. So molecularity basically helps us keep track of how many things are interacting in our system, how many things we would expect to see in participating in a transition state, sort of actually describing what's happening chemically, and therefore connecting that to a first order rate expression. So this is a unimolecular elementary step, and it has a first order rate expression. We can also see examples of bimolecular mechanisms. And so it's possible that in order to get some reaction to happen, you need two A's that interact to form whatever products. And so when you have two reactant entities, you have a rate expression of that elementary step that's second order. It's also possible to get something bimolecular with two different reactant entities. So here I'm not saying that it has to be two of the same thing. I'm just saying overall, two species, two entities, two molecules, whatever you'd like to call them, are interacting with each other and they're controlling the rate. so that this is a biomolecular mechanism where two species are participating in the reaction and in the transition state, and the rate expression is dependent on both of their concentrations, so that this step has an overall order of 2. It's bimolecular. And we can extend this to talk about something being termolecular. And so basically the exact same thing, except you can have 3 reactant entities. And so you can have rate equals Ka cubed because there's 3 A's interacting. You can have an A and 2B interacting. You could have A plus B plus C goes to something and have this be termolecular. You can have any combination of things as long as the overall rate is 3 and the number of entities or species in the system that's actually chemically reacting is termolecular. And so these are sort of the most common named ones that we'll be interacting with in this course. And so it's just good to know what this language means so that if you encounter it, you can say termolecular means that there's 3 reactant entities. And I'm looking for some expression where 3 things are combining, forming some transition state out of those 3 things, and then some product is being formed, which may be some combination of individual molecules or maybe one large molecule. And so it doesn't tell us anything about what we're producing. It just tells us about what's happening and what we're chemically feeding into this reaction in order to get something. So now we can go back to talking about how we might use these mechanisms to help us predict the net reaction rates. And we're going to make predictions, and then we're going to see if we can prove that they're correct. We're not going to predict with too much confidence, but we can certainly give it our best shot, and we can see if our experimental data confirms what we're predicting. So if we had this system, which we talked about before, and we wrote these individual rates for, and then I told you that this first expression is really slow. So it takes a long time for that ozone to fall apart and form an O2 and an oxygen. Then you might guess that the most important thing in controlling the net rate is the decomposition of this ozone. And so this is a prediction based on this mechanism. If instead I told you that the second step was really slow, maybe instead you might predict that the total rate is a function of both the oxygen concentration, the O3 concentration, and K2. And you also might get a little spooked by this one because all of a sudden now an intermediate shows up in the rate expression. And so both of these are potential predictions, which may or may not have some validity, but ultimately what I'm sort of alluding to with this sort of fast and slow is that when we look at these mechanisms, it matters what the rate limiting step is, or what the slowest step in the reaction mechanism is, because this sets the overall rate of that reaction. So if it takes a long time for ozone to break down, then the second that it breaks down, it can move forward and do other stuff more quickly. So the thing that would affect our overall speed would be the first line. If instead this oxygen reacts poorly with this second ozone molecule, then it might be the case that our system can generate a lot of this initial O2 and oxygen by itself, but then it takes a long time to get slowly converted at the end. So we can use the speeds of these reactions, the kinetics of these reactions, to help us try to predict what the speed of the overall reaction looks like. But it's important to know is that while you can make these predictions, you can't actually prove them correct. And so unless you somehow have some really fancy spectroscopy, you're watching these reactions happen in your beaker, you're seeing transition states, which is really challenging because of how short-lived they are. Unless you can do all of that, you can't prove that your mechanism and your predicted rate is correct. So we just make predictions and then see if they're plausible using experimental data. And so I'm going to work through in a separate video some example problems where I talk about sort of what this means, but we just need to be careful because when we look at these expressions, we might suggest that this rate is true, but then when we go and we calculate experimental rate data, it might tell us that our reaction rate is second order with respect to ozone. And nothing about this mechanism or either of these rate steps would suggest that it should be second order with respect to ozone. And it being second order with respect to ozone is something we experimentally measured. So maybe our reaction mechanism isn't correct. And it might be that the experimental rate that we get is first order with respect to ozone. And so that could potentially suggest that our mechanism isn't wrong. But we don't know that it's happening unless we can actually see what's happening in the beaker or in whatever reaction cell. So we're still going to make predictions, and we're still going to look at these mechanisms and try to use them to see how we would expect concentrations of each of these to change with time. But we're going to be careful, and we're going to remember that the experimental data ultimately can help us distinguish between mechanisms we know are bad and mechanisms that might be right. So we're just going to be a little bit careful here, and we're not going to say we know what the true mechanism is, unless we're talking about experimentally. We'll still make predictions because it's still useful. And so before I move into that video where I talk about how to actually sort of derive these expressions, and before I give you some sample problems, I wanted to point out another type of reaction that you might see in these systems and how we can write rates for that reaction. So far, we've only been talking about irreversible chemical reactions. And so instead of having a double arrow, we've had sort of single arrow reactions, which say that we go from reactants to products and we can't go backwards. However, hopefully by this point in the course, we sort of recognize that that's not true of most reactions. Most things are slightly soluble or can go sort of slightly backwards, or there's some equilibrium with acid and base chemistry. And so when we talk about rates, we also need to be able to handle something that has an equilibrium and something that can go forward and backwards. And luckily, we can write still the same rate for the forward reaction, where you have K1 multiplied by the concentration of NO and Cl2, if this is an elementary step. And so I'm talking about a reversible elementary step. If we have this reversible elementary step, we can write this rate for the forward reaction, and then we can flip that reaction over and we can write a rate for the reverse reaction. And we use the formatting of -1 here to say that we're talking about the rate of a reverse reaction. And if I flip this reaction over, then NoCl2 becomes my reactant. And so the rate expressions that we have look very similarly. We're just using this notation of -1 so that we know which way we're going for one reaction, forwards or backwards. And so we can have systems that go forward and backwards, and we can talk about relative rates and all of this. But if you're given a reversible reaction, and then you're told it's at equilibrium, so sort of two things, it's reversible and at equilibrium, then hopefully we remember that equilibrium means that the rate of the forward reaction equals the rate of the reverse reaction. So the reactions are still happening, but the relative distribution of reactants and products is staying stable. That's sort of what we were talking about in thermodynamics, where we have this exchange of forward and reverse reactions. And so at this equilibrium, this is true. The rate of the forward reaction is equal to the rate of the reverse reaction. And we just wrote those expressions, and we can plug those expressions in, where the rate of the forward reaction is K1 times the concentration of NO times the concentration of chlorine, and the reverse reaction is K-1 times the concentration of NoCl2. And if we want, we can rearrange this and get the concentrations on one side and the rate constants on the other side, and you might recognize this as the equilibrium expression that we derived in the thermodynamics portion of the course, where the product over the reactant is this equilibrium expression. So kinetics and thermodynamics meet for these rate expressions for reversible reactions when they're at equilibrium. And the equilibrium is going to reflect the balance of how quickly this reaction goes forward and how quickly the reaction goes backwards. And it will lead to some product distribution. And this will be helpful both to make sure we understand how thermodynamics and equilibrium are connected, But also, this equality at equilibrium can allow us to find NoCl2 concentration with respect to the rate constants and the concentrations of NO and Cl2. And so in the sample problems that I do, we'll use this sort of equilibrium expression at one point to help us write expressions in terms of the concentrations that we're interested in.